Hello everyone, today I want to talk about programming paradigms. So there are a lot of great programming languages to explore. As you can see this rubber ducky here, excited to see the code. And we want to wonder, what is this programming language, or the structure of this programming language? Where we see on the left here all the variety of programming languages like Java, Python, C#, C, Lua, as we can see in like Roblox games. There's so many applications. And so I want to cover today all of the variety of ways we can solve problems using programming languages. So overall, it's thinking like a computer scientist. I want to make sure that we can see how programming languages connect overall, and emphasis on what problems that they solve. And that brings up a question like, which one should we choose? As seeing a variety of programming languages thrown onto us like a garden hose. Alright, so let's go ahead and unleash this. So first, I want to talk about what is programming. I mean, we say programming paradigms. I want to focus on what is programming first. So programming is designing and implementing instructions for a computer. So I want to put a part in designing because we have this idea of coding and programming. It brings up to a question of what's the difference. And so I like to think of programming as the actual thinking and creating of an algorithm. An algorithm is just the step-by-step instructions for solving a problem. It's a precise step-by-step instructions for solving a problem. And so it's just like if I were a chef and I were to make my recipe, the recipe for making the let's say pasta is my algorithm, and emphasis on the actual depth of the step-by-step instructions. Because if I were to make some recipe and I just say, get out the pasta and now cook the pasta, now you have pasta, that wasn't that specific. But if we were actually specific and we said, all the materials to get out and the sauce to get out and what temperatures to get out, that really makes those precise step-by-step instructions, which is the algorithm. But in essence, programming is the thinking and creating of the algorithm. So maybe your flowcharts, your pseudocode, and etc. And coding is just that implementing part when you're creating. So it doesn't involve let's say you were asked to calculate the average of three numbers. It's not before when, let's say you were to design, like, how can I calculate the average? Or in your head, I can calculate the average by doing this and this. Well, that thinking is part of programming, and the creating part as well. And specifically the creating parts we can call coding if we were to implement the algorithm using source code. An example is like in Python, in C, and all of these different programming languages. So since we have to design algorithms that involves logic, programming languages involve logic as well. And that's why we see things like loops, conditionals, and variables. What a fun world to be in. But I mean, it makes some programming languages sad, like HTML. Oh man, I'm not a programming language. Why? Well, I thought it was a programming language before, but it's a markup language, meaning that it's just meant to label text, markup text. It doesn't have the actual logic like JavaScript over here that says I'm a programming language, where we actually have loops, conditionals, and variables. And what are paradigms? Well, paradigms are just going to be the styles or versions of solving problems using programming languages. So as we can see, there's a variety. Maybe Java, maybe Python, maybe C++. But I mean, which one should we choose? Let's explore that now. So, a way to categorize programming paradigms could be imperative and declarative. Imperative means that you code the algorithm. You have to actually write down all of the loops and the conditions to meet the step-by-step instructions that you want to follow. Whereas declarative is that you ask, and then the programming language will code the algorithm for you. So let's see that in action. So let's say that you want to ask for some data. We're going to use SQL. So you ask for some data. There will be a database that says, okay, I'll retrieve that data for you, and I'll code an algorithm to get that data. And as a result, we will get the data that we asked for. And it's declarative because I asked for it, and now the database made that algorithm to give me back the data. But imperative, we have to actually write down the step-by-step instructions, and so we can categorize those imperative languages as low-level and high-level. First off, an example of low-level is assembly. And when we say low-level, we mean like really, really precise to the level of like talking directly to a CPU or talking directly to like hardware. And it's low level because we're saying like at this exact memory address, or it's very close to machine code language, we're saying do this exact execution. So it's very direct. It's not really like human language. Whereas a high level, it's really related to human in some sense, where we can actually tell, like we can define these, we can define with variables, we can define with more clear words like this or this, if, else, and things like that, where logic can be shown more easily. So that's high level language there. And so focusing on high level languages, we can categorize these as object-oriented programming languages and procedural. And those are two paradigms that are shown in these high-level imperative programming languages. And object-oriented programming languages deal with classes and objects, whereas procedural focuses on functions. And so what's the programming goal? The goal is to have readable source code. And in order to achieve this, we can have abstraction. And abstraction is just hiding away the complex details in our source code. It's just hiding away that to make it overall simpler. And so how can we achieve abstraction? We can achieve it with something called decomposition, which is just breaking down a big problem into little steps. And an example of breaking down a big problem into little steps is with functions. So looking at the procedural programming languages, let's say that we want to determine the discriminant of two quadratics. And the discriminant, if it's greater than 0, then we have 2 real roots, equal to 0, 1 real root, less than 0, 2 complex roots. Well, I can come up with some code, and I can say that I have these 2 equations. And I could say for every equation, now let me determine this discriminant and output these roots, 1 roots or complex roots. But I have to just point out that with this, imagine we were to have 100 equations. I have to put all of those equations in there. And maybe it's not that clear to somebody that's just reading my code, because they have to see all of this complexity first. They're like, where can I look at first? What is this really trying to say? I mean, overall, we just care about the functionality. This is going to determine a discriminant. So how can I clearly and very easily see that this is going to determine the discriminant? I mean, this can look very complex as I keep adding more equations. So to hide this complexity, I can use functions, which is a key attribute of procedural paradigms, or the styles of programming, where I can take in for input a equals 1, b equals -5, c equals 6, for example, and then we can make a function that takes in those inputs, or we can also call them arguments, called determinant discriminant to the function, and we can then compute that there are 2 real roots and output to the user there are 2 real roots. So now we can make that function and just abstract all those details away, maybe hide it lower in our code or in a separate file. And in the main code, we just have determinant discriminant. And that right there shows, wow, we're good. Like, we know we're determinant discriminant, that's all. And so this is procedural decomposition, because in a procedural paradigm, we're breaking down the large problem into functions. And so what is the procedural paradigm great for? Well, it's great for direct tasks. Say, for example, I mean, I love like any applications involving electronics and software combined. So I just want to go over an example. Like, let's say you want to program your LED lights. Oh, you know, that is a direct task. So we can use procedural paradigms and abstract away details involving any complexity with turning on these LED lights, or like having some specific pattern, by just saying like animate pattern. And then in animate pattern, we can have other methods or other functions, and that will overall result in a great direct task. But it is not for lots of data and objects, which we will see. This brings up a question. What if we want to deal with larger systems? What if we want to deal with relationships between these systems, like or objects, organize the information objects? Well, we'll see an example of this. So imagine we have a complex system like the Boston Dynamics robot. All right, so let's say that we're focusing on one leg, and we're focusing on organizing the information for the motors, these actuators here. So we see that we have this red one, the knee motor, the blue one, the hip actuator, and we have this green one as well. Well, when we're going to look at this, we can categorize it as objects, which are just going to be containers of information having attributes and actions. So these attributes, or we can say characteristics, could be something like in the knee motor having a temperature of 40 degrees Celsius, having a torque of 75 Newton meters, or maybe having a velocity of 12 radians per second. And then, so those are the characteristics, and then our actions could be something like set torque and get torque. And then maybe for my other actuator, or for my hip motor, I can have something like a temperature of 45 degrees Celsius and all this other information. And maybe for the last actuator, I can also have some information with slightly different values. But do we notice something with these? They all have the same type of characteristic, and they all have the same type of action. So what we can do is group together all of these objects or containers of information of characteristics and actions into a class, which just shares characteristics and actions for other structures of data that have those specific characteristics and actions, such as, for example, temperature. Maybe now we're going to have a piece of information that sets the temperature to some value like 40 degrees Celsius, or hip motor, set it to 45 degrees Celsius, or this last motor, set it to 55 degrees Celsius, etc. And so now this is called object decomposition because we're breaking down a large problem into objects. So very similar to procedural, but instead of functions, we're dealing with the object-oriented paradigm. So this is objects. And let's bring up a new topic. Well, we have encapsulation as well in object-oriented programming languages, which just means that you are controlling the access to data for security reasons. So maybe, for example, in our motor class, we want to make the instance variables, which we call these like temperature, torque, and velocity, private, because we don't want them to be accessed by some other class. Let's say we set an object temperature to 55 degrees Celsius, and we wanted to keep it to that as its original value. Now, we don't want this original value to change, so we will just keep it as that, and we won't allow another class to modify it because like this is the constant value that defines this object, so let's make it private. Whereas maybe in another class, you're allowed to get the torque information, or you're allowed to set the torque to some value. But that doesn't mean explicitly changing the starting value of the instance variable that declared the object created. And so yeah, these are the instance variables, and functions that are inside classes now are called methods. And so the object-oriented paradigm is great for systems and complex data. So imagine you had to make a program for like a large school. Are you really gonna do that with just functions? I mean, yes, we can break down complexity with functions as well, but how can we organize all this data? Like teachers, students, admin, classroom numbers, oh my goodness, it's a lot. Or the Boston Dynamics robot. We can actually make this all a coherent system. This brings up to a point. Why are most languages hybrid? Well, most languages are hybrid. I mean, we have like our procedural and object-oriented programming as in hybrid, because there's still going to be some complexity that isn't just a large amount of data or that isn't belonging to a class. So looking back, for example, at the methods of the knee motor, set torque and get torque, those just belong to the motor class because we have an instance variable called torque, right? So the torque belongs to a motor object, and we can modify or set that value to something. But what if there is no characteristic a part of the motor class, something outside, like maybe calculating the distance between two objects or two robots, or maybe calculating average velocity? We can see that we can actually put in raw inputs, or we can put in data that's not restricted to just the motor class. So in essence, we're not saying, okay, now have these functions because we have a torque characteristic in our class. I mean, we don't have a distance traveled characteristic, but we surely can still hide the complexity and create a function that abstracts away those details. So it's great to have a mix of both, which is why Python, for example, is a hybrid, which is why a lot of other languages as well are. Thank you for listening. That is it. I hope you've enjoyed and thought like a programmer. That's all. Having a great day.